Okay, this is the continuation of video lesson 5.2. So we left off with Bohr's explanation of the hydrogen atom worked great, but it didn't work so well for other elements. Okay, Louis de Broglie uh, hypothesized that particles, including electrons, could also have wave-like behaviors. Okay, so this is kind of going, first we went from light having waves to the particle nature of light. Now we're going from um, electrons, which are very small particles, also having wave-like things. So it's going the opposite of what we were doing before. Okay, so the wavelengths, standing waves have certain frequencies that they resonate at. Okay, so that's what de Broglie was saying, or trying to say with the electrons, that there's certain frequencies that they um, resonate at, certain frequencies where they um, exist in a nice harmonic way, the way these standing waves work. And if they're not at one of those frequencies, then it's going to be not a nice pattern, and it's not going to be very stable. Okay, so the de Broglie pattern equation, predicts that all moving particles have wave characteristics. And his equation is here. It says that the wavelength equals Planck's constant divided by the mass of the particle times the velocity. Okay, so when we have this, Planck's constant is really, really small. So if we divide it by any kind of mass, even the mass of an atom, we're still going to get a very small wavelength. Okay, and if we have a very high speed, like an electron, then that's going to make that denominator um, well, the mass is small, but the velocity is high, so it could make it fairly big, but this number is so small that that wavelength is going to be. Remember, that was like times 10 to the negative 36, so it's a pretty small wavelengths we're talking about here. Heisenberg, another scientist who worked out that the uncertainty principle back from Breaking Bad fame, right? This is why Walter White chose the name Heisenberg for his uncertainty principle, and it states that it's impossible to know precisely the velocity and the position of a particle at the same time. So Walter White thought he was being clever and thought it would be impossible to know that he either is a drug dealer and a science teacher at the same time. So that's what his reference to Heisenberg was. But Heisenberg was a brilliant scientist who came up with this principle and related it to, it's more complicated than this, but for us, it's impossible to know the velocity and the position of a particle at the same time. So it's like driving in your car, right? You can know exactly what speed you're going. You look down at the speedometer and you can see exactly what speed you're going, right? But it's impossible to know exactly what position you are at the same time that you're moving along, right? Because you're moving, you're in the position. But if you take an accurate view of your position, okay, where I'm right here, it's impossible to know your exact velocity at that particular time too. So you can't know both of these at the same time accurately. Okay, so this related to how orbitals in a electron orbitals, we can't know exactly where they are, unlike the Bohr model, which said, okay, they're in this place or this place or this place. The Heisenberg uncertainty principle with the de Broglie wave equation led to seeing that the electrons exist in orbitals, and there's a probability that they'll be in certain orbitals, but it's just a probability. They don't have to be there. This is Heisenberg's uncertainty principle, right? If a photon hits an electron, then we know exactly where that is. But after that collision, the electron changes speeds and the photon changes its wavelength, so it's impossible to know where that happened. Okay, so it's impossible to know both the velocity and the speed of both the position and the velocity of this electron at the same time, one or the other. Schrodinger equation, well past what we're doing in this class, treated electrons as waves also, so we're getting back to particles being treated as waves. And Schrodinger's equation is pretty complicated, but it led to this 3D region around the atom called atomic orbitals. Okay, so we have these density maps, and the electrons are going, we can still kind of think of them as like the Bohr model with orbitals, but as long as we know that's not really the case, it's fine. Okay, so those these numbers, the principal quantum numbers, indicates the size and the energy of the orbitals, and the N represents the principal energy levels. Okay, so that's what we're talking about, the principal energy levels of these electrons. Then they also have sublevels, right? They have 4 different sublevels of these electrons. So you have main levels and then sublevels. Okay, so there's the S, each energy sublevel relates to the shapes. There's 4 different shapes of orbitals. We're doing 3 of them on this one. There's S, P, and D. And then there's also F orbitals, but they're even more complicated looking than these. So we're going to mostly concentrate on the S and the P orbitals. You'll need to know the shape of these P orbitals. There's 3 of them. They're called dumbbell shapes. It's along the x-axis, along the y-axis, and along the 3D, the z-axis. Okay, so you'll need to know that the s orbital is a sphere of varying sizes depending on the energy level, and the p orbitals are along the 3D axes, x and y. We normally think of that, but then we add a third one to get a 3D effect for the plane. Right? We have the plane plus the up and down x, y, and z. Okay. All right, so that's it for section 2. We're going to be doing a lot more stuff with the electron configurations in the next